Hello everyone, so in the previous video we were talking about end behavior and connecting the end behavior of power and polynomial functions to limits with infinity of power and polynomial functions. Right, now we're talking about how do we determine end behavior for rational functions, right? So functions where we have a polynomial divided by a polynomial. So we want to recall that as x is approaching positive or negative infinity, the function values or the output values are approaching the horizontal asymptote. So that's what was happening with our rational functions. Okay, and so we did some examples when we talked about limits graphically where you did see that. I gave you graphs of rational functions and we saw that as x went to positive or negative infinity, we saw that it was approaching that horizontal line, aka the horizontal asymptote. Okay. So if we want to know what the end behavior is for rational functions, all we need to do is use the horizontal asymptote rules to find the location of horizontal asymptotes. So here I'm recalling those rules to you for finding the horizontal asymptotes for rational functions from pre-calculus. Okay, and so they're listed here, right? We had three cases. If the degree in the numerator is less than the degree in the denominator, then the horizontal asymptote line is y equals 0. If the degrees of the numerator and denominator are the same, then divide the coefficients of the terms with the highest degree to get the horizontal asymptote, right? And then if the degree in the numerator is greater than the degree in the denominator, then there was no horizontal asymptote. Okay, so those were the three cases. Okay, so in practice 3, we want to answer the following parts for this rational function here. So looking at this rational function, what do you think the horizontal asymptote line is? Well, hopefully you would say that the greatest degree in the numerator is 2, and the greatest degree in the denominator is 4. Okay, so looking at these terms with the highest power, all right, we see that since the degree is bigger in the denominator, that the horizontal asymptote line is just y equals 0. Okay. So now if I want to consider the end behavior, we have that as x approaches infinity, f of x is approaching 0. And as x approaches negative infinity, we have that f of x is approaching 0. Okay, so from both directions, as x approaches infinity and as x approaches negative infinity, the function or the output values are approaching that horizontal asymptote line. So in other words, they're approaching 0. And so writing this using limit notation, we would say the limit as x approaches infinity of f of x is equal to 0, and the limit as x approaches negative infinity of f of x is equal to 0. Okay, so hopefully we've made some connections here in terms of the pre-calculus talking about horizontal asymptote lines, the end behavior, and now connecting it to the calculus with the limit notation. Okay, so in practice 4, I just wanted to now straight up just give you some limits, and so hopefully we can figure out now how to find these limits using some pre-calculus. Okay, so if I want to find the limit as x approaches infinity of this polynomial, what I need to do is think back to the shape of it and talk about end behavior. So here, I know that the end behavior of this polynomial is going to be the same as the end behavior of the term with the highest degree. So really, I'm going to draw a rough sketch of the shape of this power function. Now I'm going to note to you that doesn't mean that the shape of this power function negative x to the 5th is going to be the same shape as this entire polynomial negative x to the 5th plus x plus 9. Alright, what I'm doing is I'm just going to draw the power part so that I can get an idea of the end behavior for this entire polynomial. Okay, so here, drawing this, I know that based on the graph, it's going to look like this, based on my chart, sorry. So, as x approaches infinity, I know that f of x is approaching negative infinity. Okay, because I'm looking to the right of my graph, right? And I can see to the right of my graph that the function is pointed downward. And so that means that this limit is just going to be equal to negative infinity. Okay. Now looking at part B here, right? So I want to figure out what this limit is. Okay, and so we can see here that this is a rational function, right? And so like we talked about for M behavior of rational functions, we just need to find the horizontal asymptote line, and then we knew where it was going, right? If we found that horizontal asymptote, then we knew as x approaches infinity, the function is approaching where the horizontal asymptote is. And then same thing as x approaches negative infinity, right? So looking at this, you want to find the terms that have the highest degrees here. And so the highest degree in the numerator is 5, right? And so is the highest degree in the denominator. So they, the numerator and denominator have the same degrees here. So I'm looking at these two terms, negative x to the fifth and 3x to the fifth. And so in this case, since their degrees are the same in the numerator and denominator, then I need to take the ratio, right, of the coefficients. I need to divide those coefficients. So I know that this limit is going to be negative 1/3. Okay, because for M behavior, as x approaches infinity, f of x approaches 1/3. And then as x approaches negative infinity, f of x approaches 1/3. Okay, the last thing I want to talk about is basically just defining formally now using calculus what a horizontal asymptote is. So here I'm saying the line y equals L is a horizontal asymptote of the graph of the function f if either the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x equals L. Okay, so now let's consider this my AP question. So let f be the function defined by f of x equals 1 minus 5x minus 2x squared over 3x squared plus 7 for x is greater than 0. Which of the following is a horizontal asymptote for the graph of the function f? Okay, so we know here how to find that, right, using pre-calculus to look at the degrees of the numerator and denominator. And so hopefully you see that their degrees are the same. So now I'm looking at this negative 2x squared and then this 3x squared here. So I know that y is going to be equal to negative 2/3. Okay, and so this would be my horizontal asymptote. All right, another note that you want to make is that if I consider the limit as x approaches infinity of f of x, that would equal negative 2/3. And then if I consider the limit as x approaches negative infinity of f of x, that would equal negative 2/3 as well. Okay, and so here in this case, you would see that we have proof for our horizontal asymptote, right, using the calculus and then also using the pre-calculus, right, to find them. So either piece you could just say, okay, well I know from pre-calculus the horizontal asymptote is y equals negative 2/3, but then now using the formal definition from calculus, when I consider the limit as x approaches infinity and the limit as x approaches negative infinity, I know that I'm going to get negative 2/3 there, and so therefore that's a horizontal